Hey everyone. So we're continuing studying this classification theorem that says all surfaces of a certain type, so no boundary and with finite volume. So basically, the way you should think of this is all surfaces that can be represented as a polygon where we've identified edges. All of them are topologically equivalent, so up to stretching, are equivalent to one of the following three types. Okay, so that's really nice. And we want to talk about how to prove such a statement. So the idea is given a surface, which again is represented by a polygon with edge identifications, what we want to do is a sequence of cutting and gluing moves, as we've been practicing with for a while now. So we can perform a sequence of cutting and gluing moves to get this polygon into one of the forms above. So what are the forms above? Well, let me maybe work backwards. So a sphere, S2, another word for the sphere, as a polygon can be represented as a loon where I glue the edges without a twist, right? You'll notice that if I glue these together, I get a football which can be stretched to give me the sphere. So anyway, maybe I should say it's topologically equivalent. RP2 looks like a loon with two edges glued together with a twist. It's topologically equivalent to that. And so a connected sum of those, if I have a bunch of them, remember that the connected sum just, what you end up doing is take your polygon and, take your many polygons and put the edges all together. And so for instance, if I had one RP2, another RP2, however many, then the connected sum of these, let's say I just had three of them, I guess. So this one would look like, I just start going through the edges one after the other. So first I do the two blue edges, then the two red edges, and then the two orange edges. So this is what the connected sum looks like. And maybe it'd be better if I just for simplicity had all the arrows going in the same direction. So a connected sum of RP2s, n RP2s, looks like a polygon with two n edges where pairs of adjacent edges are glued together, like that pair, that pair, that pair, and all the gluings happen with a twist. Okay, and so that's how I get RP2s. And then connected sum of tori, well, torus looks like this. It's got two pairs of edges glued with no twists. And so a connected sum of those ends up just being maybe I'll do it really simply. So 1, 2, 3, 4 edges. 1, 2, 1, 2, 3, 4 edges. So let's see. These blue edges get glued with no twist, which means they're pointing one's clockwise, one's counterclockwise. And similarly like that. So all that matters is the relative directions, right? And then the other torus is the same. So I've got something like this. Okay, and so connected sums of tori, if you connect some n tori together, what you're going to get is a polygon with 4n edges, where every 4 edges have this pattern of blue, blue pointing the other way, red pointing the other way. And then, another 4 and another 4 and another 4 with that same pattern. And so the goal is, if I give you a random polygon with random edge identifications, that you can do cutting and gluing to convert it into one of these 3 shapes. Okay? And we started talking previously about how to do this. So there's kind of a sequence of moves that we can do. So moves, let me be careful here, moves to convert a given polygon to something of the form above. Okay, so the first move we saw is you look at your big polygon. It's got many edges. And I'm just labeling this collection of edges in X and Y, but let's say that there's a pair of edges that you see somewhere on the polygon that get glued together with a twist. So you see something like this. Then that looks like it should be coming from an RP2, from a projective plane, but it's not obviously of that form because connected sums of RP2s have adjacent edges being glued together with a twist. And here these aren't adjacent. And so the cutting and gluing you can do is the following. I can cut across between these 2 edges, and then I'm going to glue the 2 pieces along the red edge. And so if I do that, what do I get? Let's see here. So I'm going to move it over a little bit. So I'm going to cut this part off. And you'll notice I need to flip it, right? For these red edges to glue together. And so if I did that, what would it look like? Well, the Y would come out here. And since I flipped things, the direction of the arrows may have changed. And so you have to be careful when you do this in practice. You have to look at what these actual edges are and what happens when you flip them. But anyway, this X set of edges is going to get glued to the Y set of edges. And I flipped that picture, and so this purple arrow is now pointing down. Okay, so that's what it looks like. And I can stretch this out. So these are the same. I haven't changed anything yet. But then I can stretch, which is why I'm using the equivalence sign, to get the X edges are glued to the Y edges. And then I have these 2 pieces. Okay, and so this is helping me in my goal of trying to get to one of these 3 forms, because at least part of my polygon now has 2 adjacent edges glued with a twist, which I can recognize as being an RP2. And so this is really the same as this surface xy connected some with RP2. Okay, and so we're getting closer because we've simplified things a little bit. All right, so that's the first sort of move that one can do in trying to prove this theorem is if you see two edges glued with a twist, like these red ones here, there's a new way of representing it that involves some stretching that converts it to something where you've got two adjacent edges glued with a twist, which is of the form we want. Okay. The second move, which can be done, is one involving the torus, right? Because we also might have tori in here. And so let's say you see what looks like it should be a torus when you're looking at your polygon. And what I mean by that is you've got two pairs of edges being glued with no twists involved. But it's not a torus because there may be a bunch of edges in between all these. So our goal is, again, via a sequence of cutting and gluings, to convert this into something where we see the torus as one part of this polygon in the sense that we've got four adjacent edges that have the pattern of a torus. In other words, we've got something like this, right? Four adjacent edges where you're gluing sort of opposite pairs and there's no twists involved. Okay. So to figure this out takes a little bit of work to figure out how to convert this into the form we want. But it turns out to be a good idea, just through trial and error, to cut right there. So cut between one of the pairs of edges. Okay, and so if we do that, then I can reglue along the red edges. And so what do I get? Well, all right. So I get this part, and I'm going to glue this to it along the red edge. So I get that. Okay. And why is this an improvement? Well, now I have three edges next to each other, where previously none of the four were next to each other. But I've still got to do a little bit more to get all four next to each other. So first I'm going to stretch this a little bit. So I've got the two purple edges, got these two blue edges, and then I've got, let's see, W, X, Z, and Y. That's the part we don't know what it looks like. Okay. And what's the next thing to do? Well, I'm going to do sort of the same move I did before, which is cut from the top or the bottom of a pair of edges. And this time I'm going to do the purple edges. Okay. And so if I do this, then I can reglue the blue to the blue, right? So let's see what I get. So this is equal to, I can just copy this part. And then I want to glue, move that over. I want to glue this piece now along the blue edge. And so I'm going to stretch things a little bit. So I should use a equivalent sign. So if I glue along the blue edge, well, here the blue edge, the back of the blue edge is connected to Y and then Z. And so I have Y here and then Z there. And after Z comes the orange edge, which gets glued to the front of the blue. So there's the orange edge there. And so I can stretch this to get something simpler. So I've got z, y, x, w, and then coming out of that, I have exactly what I want. I've got 4 edges, which are all adjacent to each other, glued with no twists. And so this, we can see, is exactly what we wanted. We have something with fewer edges, connected some with a torus, because this is exactly what it looks like when you connected some a torus onto something. Okay, and so again, this is useful because we now have a piece which looks exactly like one of the pieces in our theorem. Looks like that. Okay, so that's another move. And then there's one other, because so if you've been paying attention really closely, you realize that there's one situation which may arise, which we haven't dealt with yet. So what if we have the following? Some edges over here, some edges over here, and a pair of edges that are glued with no twist. Okay, well, this looks like the torus situation, except we may not be able to find another pair of edges in between there to actually create, you know, the 4 edges that a torus has. So we're kind of stuck, you know, unless there was an edge over here that was getting glued to an edge over here with a twist, then we could do move 1 to simplify things. But what if that doesn't happen either? So if neither of those things happen, then we have this picture. But there's no edges of x getting glued to edges of y. Because if there were, then we'd be in a situation where we could do 1 or 2. But if we can't do either of them, what that means is that there's no edges of x glued to edges of y. Okay, what does that mean? Well, if you think about it, what's the best way to say this? If I take just the x part here and just the y part here, those give me 2 surfaces all on their own. Why? Well, because none of the edges of the x sides are getting glued to edges of y sides. So all these edges are getting glued to each other. All these edges are getting glued to each other. And so they're coming from their own polygons because there's no gluing from this side to that side. Okay, and so I've got this polygon x and this polygon y. And what is this part doing? Well, one way to think of it is, trying to think of the best way to say this. Here's a way to say it. I'm going to do some cutting. I'm going to cut there. I'm going to cut there. Let's see what we get then. So if I do that cutting, I'm really just going to break it into its pieces now. So on the left side, I've got all the x edges. And I've got this edge here, right? But notice, by the way, that this vertex here is getting glued down to here. And so this is actually forming a disk. This orange edge is a disk. So this point's glued to that point. So another way to represent it would be as follows. got all the X edges. And I've cut a disk out here. So I've got X minus a disk, right? And this orange edge is going to get glued to something, which I haven't drawn yet. What's it getting glued to? Well, it's getting glued to this shape here along this edge, along that orange edge there. And then same thing with Y. I can think of this part here up to stretching as a surface or a polygon whose edges are Y, the edges of Y, with whatever edge identifications are there. Together with, I've removed a disk from here, and it's getting glued to that middle piece. Okay. Now let's think about this middle piece for a second. I'm not gluing the left and right edge to each other, right? Because the left edge is getting glued over here, the right edge is getting glued over there. But I can express this more simply by gluing the top and the bottom edges together, and that's giving me a cylinder. And so I could think of this as a cylinder. Where these circles here are getting glued to these circles here. Okay? And so what does this look like? You know, what does this surface look like? Well, I've got this surface given by the left-hand side, and I've cut this disk out of it. I've got a surface given by the right-hand side. I've cut a disk out of it. And then I'm gluing these two disks together with a cylinder. So I'm gluing the X surface to the Y surface with a cylinder. So let me actually draw pictures of these surfaces. You know, maybe, well, it doesn't look too different from my other surface, but locally I've got some surface like this. I don't know what happens over here, but that's X. Got some surface Y like that. And what I'm doing is I'm cutting a disk out of here, cutting a disk out of here, and then I'm gluing them together via a cylinder. Well, if you think about it, up to stretching, this is the same as just doing the connected sum, right? This is the same as taking X and taking Y, cutting circles out of each, and then just gluing those circles together. Just moving this over and gluing the circles together. Why? Well, because I could stretch this bottom picture out so that where they were getting glued together stretches out and it gives me a cylinder. Okay? And so what I'm trying to say is that this is the same as just taking the connected sum, this, of the X side with the Y side. In other words, up to topological equivalence, this cylinder that I've added doesn't make any difference. And that's what these two red edges are representing. They're representing a cylinder in between the left side and the right side. Okay? And so the third move is 3. Whenever you have X, Y, with two edges glued with no twist, and this part's really important, no edges from the left side are glued to edges of the right side. So this part's important because that's what allowed us to say that the left and the right were giving their own surfaces. But whenever you have this situation, it's the same. You can replace it. It's the same. Yeah, I'll write what I had before. You can replace this by just removing those edges. And you haven't changed your surface. This move does not change your surface. Up to topological equivalence. They're related just by a stretching. Okay. I claim that with these three moves, we're almost done. So you remove pairs of edges whenever none of the left side's getting glued to any of the right side. Whenever you see what looks like a torus, except they may not be adjacent to each other, there's a sequence of moves that actually converts this into something where you do have a torus connected some with the rest of it, and similarly with the RP2. So to finish the proof, doing these three types of moves repeatedly you can reduce things until you've been able to represent your surface as well. I mean, what does it do? It collects RP2s and it collects toruses. And so if you do these moves enough times, eventually what you're going to end up with is a bunch of toruses connected some with a bunch of RP2s. And we don't really know what the order is. Just a bunch of toruses and RP2s. Okay? Now this isn't quite the theorem, because the theorem says it's either all toruses or all RP2s, right? So we're not quite done yet, because this is toruses connected some with RP2s. So what's the final step? Well, if there are no RP2s, in this representation, then we're done, right? Because then we've just got a bunch of toruses. If there are, then we can simplify further. Because every time we see a torus connected some with an RP2, you know from your exercises that that's topologically equivalent to a Klein bottle connected some with an RP2. But a Klein bottle, as we saw in a previous video, is just RP2 connected some RP2. And so what we get is the connected sum of three RP2s. So every time you see this, in this description, something like that, you can just replace it with three RP2s. You can do this until it's all copies of RP2. Okay, so that's the proof of the theorem. And I guess there's one There's one other possibility, which we didn't mention yet, which is that after doing all of these moves, what you end up with is just a single pair like this, which of course, or you could end with this one. But that's just the third possibility, that you had a sphere to begin with. Okay, and so that's the strategy, which allows you to reduce any polygon with edge identifications to one of these three types. So what I would encourage you to do is play with this. Take a random polygon, don't make it too complicated, maybe 6 or 8 edges, and do the moves that we've talked about in this video until you've reduced it to one of these three types, and you can say where it stands in this classification. All right.